morning. Thank you very much for coming. What a lot of people have come to hear about complexity in the new machine age. So I have to say I'm quite proud of this title slide. At Java 1, I had more than one person actually took a look at the title slide and left the room before the talk even began. That's the fastest I've ever managed to piss people off. It's a record. Okay, so right. So I'm going to talk about complexity, but it's not actually that complicated a talk. But the idea of this is the background slide there is actually an extract from Knuth's famous book, The Art of Computer Programming. I'll talk about that during the talk. So who am I? I'm Maurice Naftalin. If you've heard of me at all, it's because I've written a couple of books about Java, and I like to say that the advantage of writing books about Java is that you get to speak about them, not just once but twice over. First of all, you've written the book, and so you can talk about what's in the book. And then a few years later, you discover all the things you should apologize for that you wrote in the book, and you can do another round of talks where you say how sorry you are, you got it wrong. So this talk actually comes from stuff that I wrote in the collections chapter, the collections section of the Java 5 book. It's mainly about generics and collections. I wrote the collections stuff, and in particular, I was interested in the performance of collections then. I've become more interested since, and that's what this talk is about. So I'm these other things, Java Champion and this other thing that Oracle have invented, and I talk at Java 1 as well, so that's those things. But we're not here to talk about me, or only insofar as that what I learnt about the book. So this talk is sometimes called Not Your Father's Complexity, which is a much better title because it gives me some good jokes. Because the idea of this is then I can actually say, well, right, who was your father? That was the original title. The idea of the talk is to get you to think differently about program performance, because most people are still thinking about program performance in the way that I was certainly brought up to think about it, which was that the number of instructions that a program executed was a proxy for how fast it would run, or for the cost of running it. And although obviously that is still true, a program that has to execute an awful lot of instructions will indeed take an awfully long time. It's not the only measure. Well, you knew that already, but quite often it's not even the dominant measure. So we need to change this and think about it. So the jokes are about who your father really might be. Well, I mean, not in a biological sense. So your father, in the sense of the opening slide there, was Don Knuth, who used to be and still ought to be really a very famous person indeed. He was foundational in a whole number of ways in our subject, not least that he created tech, and he did many other things as well. But in particular, he wrote this fantastic, I was going to say book, but series of books, which he's still writing, called The Art of Computer Programming. And The Art of Computer Programming, if we're going to get there, there it is. How irritating. Right, so we'll have one more go. How about that? The Art of Computer Programming. And in this, he talked a lot about performance and actually really didn't establish single-handedly, but gave a huge stimulus to the science of algorithm analysis, whereby you could actually work out how long a program was going to take to execute in terms of the number of instructions that it was executing. So this has become the big O analysis, the asymptotic time complexity analysis of programs has become a very favorite academic subject, more so in the United States than here, where they just love it, and they spend a lot of time thinking about all the different hierarchies of time complexity, most of which there's infinitely many of them, most of them represent totally infeasible programs. We're always interested, as programmers, we're always interested in performance, more so than I think we should be. I mean, usually performance, which everybody's really preoccupied with it, and almost all the time performance experts will say, you shouldn't be thinking about this. What you should be thinking about is writing good code, writing code that's going to be readable and maintainable. and in a consistent style. And to give Knuth his credit before I leave him, I would just like to say that he actually believed the same thing as well. So the bottom line, the one that's really famous here, is he says we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. So there's another story here which I would talk about if I was talking about performance tuning, which is premature optimization is virtually any optimization you do before you've actually measured what is happening in your program. Developers have a really poor idea, by and large, a very poor intuition about where their program is spending most of its time. So actually understanding the behavior of your program and its behavior in the system as a whole, in terms of the overall health of your system, is really vital before you start doing optimization. But hey, this is actually a talk about performance, so I have to talk about performance. I'm telling you that we shouldn't be thinking about it, or not very much anyway. So what was computational complexity, the standard measure by which we thought about how good algorithms were? Well, the Wikipedia definition says that it's a function which essentially represents a bound on the number of steps that a program will have to perform. It's a bound as the size of the data set for the program grows. So if you could imagine the red wavy line here is the number of steps that f of n will have to take, that an algorithm evaluating f of n will have to take. It's the number of steps it'll have to take as n increases, and above some certain k, that should be m. A sufficiently large data set, you can establish a function. This one here, Cg of n in this case. Well, g of n in this case is the algorithmic complexity, and this function is going to grow faster than the number of steps that the algorithm will have to execute. In other words, it represents a bound on the execution. So here's an example that I took at random from The Art of Computer Programming. For a multi-list insertion sort, Knuth calculated with extreme precision that the number of steps it would have to take is this: 3.5 n squared plus 24.5 n plus 4n plus 2, where n is the number of elements of the lists being sorted and m is the number of lists. So actually, this kind of analysis is interesting, but most of the time what we really care about is how is our program going to perform for large data sets, because we don't really care very much about small data sets because computers are fast. So we only really care about the n squared term, because that is going to grow faster than any other, and it will come to dominate this expression for a sufficiently large n, and so that's the one we care about. Now, the constant factor in this case, the constant factor is 3.5, but by and large, we don't even really care very much about that. What we really care about is the intuition behind the big O measure is what will happen if we double the size, or what will happen if we triple, or whatever. But I talk about what will happen if we double the size of the data set. So there actually aren't all that many different levels of algorithmic complexity, despite the fact there's an infinite number of them. And if you look this up as an academic subject, you'll find that there are books written about the infinite variety of time complexities. We're really only interested in a very few of these. Order 1 is constant time, so like a hashing algorithm, looking up in a hash table under good circumstances. Order log n, which is like searching a binary tree. Order n, which is linear search along a list. And order n log n, which is typically for sorting algorithms, right? And these are the only ones that we're really interested in, because beyond this, we're actually getting to algorithms that will be infeasible for large data sets. So everybody's favorite first sorting algorithm, bubble sort, is order n squared. And for large n, it's really not going to work very well at all. So we only really care about these because the effect of doubling n for the size of the data set for these four is manageable, although of course even for ones near the bottom of the table, it's still acute. So I always knew about this. So when I came to writing the collections chapter, I assumed that I could just apply this in a simple way to the way that to an understanding of how you should use a Java collections framework. So I got some good education about this from another candidate for your father. This is a kind of, maybe Knut got your grandfather, he's old enough to be. Here's a man who's about the right age perhaps to be your father. This is Josh Bloch, the author of the Java collections framework, the original author of the Java collections framework and the author of Effective Java, so you've probably heard of him. So he was a huge influence on me because I was fortunate enough to get him as a reviewer, a technical reviewer for the collections section of that book, and he was a very, very severe reviewer, I must say. You know, a typical comment from him would be about something I'd written. This is totally false and misleading. That was kind of medium. The severe ones were really severe, but it transformed. You want severe reviews because it was incredibly thorough and it really did a huge amount for the quality of the book. So one of the things he did was I had diagrams like this in there, and he said you don't want to tell people stuff like this at all. So there's a lot of abstract collections in here. When you often see in books that explain the Java collections framework, they often cover the abstract collections, which you'll find are mostly packaged private, I think. No, they're not packaged private. Sorry, they're public, but they're there for a particular reason. They're there as assistance to other implementers, besides who want to provide other implementations of the collections. Third-party implementers, and they give them a starter implementation with some of the operations implemented. And he said, don't bother people with those. That's for implementers. If for client programmers, all you need to care about are the interfaces. So the things in blue are really what's important. And I learned from this that what you should do is the design motivation behind the collections framework was you choose your interface according to the function that you want. Do you want a list or do you want a set? Well, you know which of those two you're going to want according to the requirements of your application, and then you should choose the implementation on the basis of the usage scenario that you have. So there's kind of standard example is that if you know that you're going to need a list, and you know that you're going to be doing a lot of insertions and deletions from the beginning of the list, then according to Big O analysis, that should tell you that an array list isn't good news for you, because insertions and deletions from the beginning of an array list, which is zero indexed, means that all the elements have to be shuffled up and down for each operation. So this advice is actually probably more theoretical than practical, because the implementations in the Java collections framework, at least, for lists, and you don't have an awful lot of choice. And copy and write array list is kind of specialized anyway, so it's really between array list and linked list. And I'll have things to say about linked list later on, but we'll get there. The idea that an array list is better for some operations than others, and a linked list is better for some than others, actually sort of works if you look at this table. If you want random access into a list, then you should choose ArrayList, because that actually implements random access efficiently. It's order one, constant time. But to get an element from some arbitrary position in a linked list means you've got to do a linear search. On average, you're going to have to go halfway down the list. So that's order n. But if you want to remove an element from the beginning of an array list, that's going to be order n, because you're going to have to shuffle all the elements down. Whereas for a linked list, all you've got to do is add a cell onto the beginning and just do some pointer swinging. So it looks like this makes sense that you ought to be really choosing your implementation on the basis of your usage scenario, which of the different operations are going to dominate in your particular application. Well, did this ever make sense? in this particular case, probably not, by the way. The idea certainly does make sense on the basis of some assumptions, like you can ignore constant factors. So, for example, all that shuffling that you have to do with an array list is actually that's an operation that's intrinsified. It's compiled as native code, and it's really fast. So even though it is order n, it's order n with a very small constant factor. So that is going to make a difference sometimes. But we allow for that. It assumes that all instructions have the same duration, and we know that's not really true because division takes a lot longer than addition. There's an assumption that memory doesn't matter, and I'll have a lot more to say about that. And the biggest assumption of all is that instruction execution dominates performance. So these actually aren't totally unrealistic assumptions. I'm not here to criticize or I'm not here to bury time complexity analysis, but I am here to maybe sort of say something more about it. In particular, that last one. Did instruction execution ever dominate performance? Well, actually it did. I mean, of course, it was only one factor. There were always these other factors, disk and network, garbage collection for dynamic runtimes, obviously, resource contention. I mean, these were always real things in any performance analysis. And there's always this problem, you know, that when you get rid of one bottleneck, if you imagine your application as being a flow of data, then there'll always be one limiting bottleneck. And when you take that away and you think, well, this should be a really nice run after this, then usually what happens is you reveal some downstream bottleneck, which may even get worse as a result of you doing that. But all the same, it was a good starting point for understanding what programs did. What it was based on, the idea that that instruction execution dominated performance came from this really simple model, which was how I learned about computers and how I thought computers worked for decades after I started, which was a very simple one, which was that the control unit, it used to be just one control unit, you didn't have any idea of more than one control unit within a CPU, would retrieve instructions and data from the memory over the north side bus and would execute the instructions on that data in the ALU and store the results back in memory, typically. And so the number of instructions was the bottleneck was in the ALU. I couldn't help when I was writing this talk. I couldn't help going and finding some pictures of pre-1980 computers. So nobody will recognise this, but it really strikes a chord with me. That was something called a machine hall, and you had it was in the first place where I worked. It was there was a machine hall which was maybe 3 or 4 times the size, about the width of this room, and about 4 times the length of it, and it was stacked full of machines like this with big tape drives and big CPU cabinets, and probably the power of everything that was in that room would be about the same as a phone in your pocket now. And actually, I had to go further than this because I also found adverts for the pre-1980 computers, which tended to look like this. For some reason, the adverts always had the computers out in the garden. I don't know why, but they do. And there was always another feature to these adverts as well. There was always a decorative woman in them. But I had to look quite hard to find one in which she was in as chaste a pose as this and with as many clothes on as that. You wouldn't believe what those adverts looked like. You so couldn't get away with that now. A friend of mine, Heinz Karberts, warned me that even putting this up was liable to get me into trouble. So why am I talking about pre-1980? The reason I'm talking about it was because at that time, memory cost about, in the 1970s, memory cost about $1 per byte. You have to think quite hard to take that in. That's a lot of money compared to the cost of memory now. So between the end of the 1970s and now, the cost of memory has gone down like that, really dramatically. And of course, this is a logarithmic scale, so we're talking about a 100,000 factor decrease in the cost of memory. And this really made a big difference to what was worthwhile analysing in terms of the cost of executing programs. So over here, prior to 1980, algorithm analysis might have been interesting, but it wasn't really very relevant because you spent most of your time. Memory was so expensive that your working memory was pretty small, and the result of that was that you spent most of your time paging backwards and forwards from disk. As the cost of memory came down, we got to the golden age of time complexity analysis, when memory was large enough to be worth for you to be able to execute large sorting and searching algorithms in memory, and so the time complexity really became the thing to look at. And then something happened. Well, what happened? What happened was that at the same time as the cost of memory was going down, the performance of memory was going up, which is very cool. I mean, that's a pretty big increase. That's a factor of 10 over 35 years or so, which most technologies would be very, very happy to have. I mean, if cars were going 10 times as fast, we probably wouldn't be very happy if cars were going. You know what I mean? You know what I mean? It's a great performance for a technology, but something else was happening at the same time. The speed of the processors was going up very much faster. And what this meant was that architectural diagram that I put up at the beginning there doesn't work anymore because you can't get the data and instructions from memory fast enough to satisfy the processors. How are you going to bridge this gap? Well, the answer is the way that you bridge that gap is with caches. So the idea is that we've got the memory is slow, and the memory bus is pretty slow as well. So you get as much as you get the data and instructions you think you're going to need into typically there's a level 3 cache. There's not always 3 levels, but most modern hardware there is. And then you promote it to the level 2 cache. And finally, up here you've got the level 1 cache, which is very close to the processor. It's on a very fast bus. It's small because it's expensive, and you can't get very much of it on there as well. I mean, the speed of light is actually a major limiting factor in chip design. So the memory hierarchy, which people often talk about, is something like this. So at the bottom you've got something very slow and also very cheap, and at the top the processor can get access to the level 1 cache really quickly, but the level 1 cache is of necessity very small, both because it uses a lot of power, because there isn't room for it on the chip. There isn't room for a lot on the chip, and because it's very expensive. So the way that I sometimes describe this is to imagine that you've got that the processor is like a person standing at a cooker boiling eggs. I chose the example to include boiling eggs because everybody knows how long that takes. If I'm going to tell you, as I will do, that say on this machine that the length of time it takes to retrieve a data item from memory all the way to the processor is about, say, 100 nanoseconds, you're going to think, well, that's really quick, isn't it? So, roughly speaking, if you talk about this machine here, mid 2013 MacBook Pro, I think it's a 3 gigahertz processor. So we're talking about a third of a nanosecond up here. And we're talking for each level that you go down in the hierarchy, on the hierarchy of caches, not down to here. It's about a 4-fold increase, roughly. So the level 1 cache is about 1 nanosecond, 3 times as much. Level 2 is 4 nanoseconds. Level 3, 16 nanoseconds. We're going up by a factor of 4 each time, except when we go from level 3 to main memory, it's much more. It's from 16 to about 100. So basically, it takes about 300 times as long, roughly, to get data from the memory as it's going to take to execute a single instruction. So if I imagine my man here, or woman, boiling eggs at a cooker, so I've got the cooker here, and I'm taking the eggs that are being given to me. We'll find out how in a moment. I put them in the pan, I wait for 3 minutes, and that's the instruction executed, and it's done, and then I get the next one. If they had to come all the way over from the fridge, where they're kept in memory, that's about 300 times as long as the 3 minutes it's going to take me to boil the egg, which is about 900 minutes, which is what, about 16 hours, 15 hours, something like that. So if there's a cache miss, and memory and data has to come all the way from main memory, I'm drumming my fingers here for 15 hours waiting for something more to work on. If you put it in a human scale like that, it's really a long time. And don't get me started on how long it takes if the data's not in memory, but you have to go out to the disk for it, because that's like, it's not in the fridge. We don't have the eggs in the fridge, we've got to go out to the shops for them. And that's about another, roughly speaking, another maybe 1,000 times as long. So basically I'm waiting like 3 years for the eggs to come from the shop. So processors are really, really fast by comparison to almost every other component of the system. And the dominating requirement of modern hardware is to keep the processors busy. You don't pay all that money for expensive processors and then expect them to stand cold all the time. So if you do any performance tuning, then that's looking at processor utilization is a really major part of the job. Now, how's this work? Well, the way I like to think about this, that obviously I don't normally expect to wait for data to come from main memory. I don't really expect to wait 15 hours before I can boil another egg. I expect to have it handed to me directly from level 1 cache. So it's like I've got a chain of helpers, like in this the conventional idea, in the old Westerns, but this is an Eastern, this is a Mongolian stamp from 1977, and how you put out a fire in Mongolia, and you pass the stuff hand over hand. Only really, to be an accurate diagram, there should be a lot of these guys right at the stream, and they should be relatively slow compared to these guys up at the fire who are really fast. And that's the picture of how the data gets to me. And it's obvious that if there's a cache miss, in other words, if this mechanism stops working, everybody drops their bucket and the whole pipeline has to be refreshed again from scratch. That's going to be a big performance overhead. And in fact, you don't need very many things like that. You don't actually need many cache misses for cache performance to come to dominate overall performance. So typical programs have about 95% hit rate. The hardware architects are really clever about predicting what data is going to be needed, because they've got to try and figure it out in advance of the processor needing it. So there's a lot of stuff about, like, for example, I'm going to talk about stride fetching. There's something as well, which I won't talk about, called speculative execution, where what you do is you just say, well, every time we came to this branch in the program before, this is the way it went. So I'm going to assume it's going to go that way again. And that way I can predict what's going to happen. And sometimes, obviously, your prediction will be wrong. You've got to throw it away. But it's worth doing that, because if that works 95% of the time, then throwing it away one time in 20, throwing your results away one time in 20 is worth it. But the other 5% really hurts. That's the stuff that's really that will come to dominate performance. So this talk is about cache misses in particular. So what are the reasons that we get cache misses, that this mechanism stops working? Well, there's two that I'm going to look at. One of them is just there's insufficient capacity in the cache. Another one is that prefetching doesn't work properly. So let's talk about prefetching. How does that work? Prefetching actually works in something like the way you might imagine. Here we've got the processor, and we've got a bunch of 64. We've got a bunch of cache lines. That's what the unit of memory in caches is called for some reason. But sometimes it's called cache stores, which is a bit more comprehensible. And the idea is that obviously there's a correspondence between these cache lines, which are typically 64 bytes in length and have to be refreshed as a whole, right? You can't say, well, I just want to refresh that particular location in a cache line. The cache line as a whole has to be refreshed. And so you've got however many of these, and they mirror what's in main memory. I've missed out. This is obviously a very simplified diagram, because I missed out the level 2 and level 3 caches. The full architectural diagrams of how a modern machine work are really quite hard work. They're big. They're very big. So the way that stride fetching works is really pretty. It's quite intuitive, though obviously the implementation's quite impressive. So supposing you're traversing a list, traversing, say, an array of primitives. That would be a really straightforward example. Then you're looking at successive locations of memory, and the processor can see that that's what you're doing. So there are algorithms written into the hardware, burned into the hardware, where they say, okay, I can see what's happening here. I will predict that he's going to keep going, or she's going to keep going, and so it can say, all right, this one, I'll load that location, or, I mean, it's obviously not a single location. Again, I'm simplifying again because it's going to load 64 bytes at a time, typically, and that's called a prefetch. And if you and for regular access to data, it really helps your cache performance an awful lot. So we'll look at what happens when that isn't the case. I mean, I can give you a clue already. I mean, if you think about how things really work in Java or any object-oriented language where we're making very extensive use of pointers, and most of the time we don't have that much control over how our data's executed, how our data's arranged, it may well be in pretty arbitrary places in memory. Right, so I mean, if you add another cell to a linked list, where's that cell going to be? Where's that cell going to be allocated in memory? Well, you don't know. And where is the data that it's pointing to going to be allocated in memory? Because everybody's pointing to data in some other place. And so this really frustrates stride prefetching. And that's going to make a really big difference to your performance. And it actually gets a bit worse than that, because the memory is divided into 4K pages, and well, typically 4K, and these and the processor is using virtual memory. So the processor knows which page a piece of data belongs to, but it doesn't know its absolute location in memory. There's a number of reasons why they do this, but the one that's most intuitive is that the processor wants to know that you aren't you haven't gone over a process boundary. Right, so it needs to know which page the data is being fetched from, so you can't so that it can check that you're not fetching data that belongs to another process. So somebody's got to do the translation between the virtual address, which is the page index and the offset within the page, and the absolute address, which is where the hardware is going to have, where the cache is going to have to retrieve it from. So you've got this thing called a translation buffer, sometimes called, for reasons I don't know, a translation look-aside buffer, but you may see that name. And that's just a cache for the page table. Obviously, this translation here is done by a structure in memory, in the native memory for the operating system, which knows how virtual addresses translate into how page indexes translate into physical addresses. But clearly, if you had to retrieve the page table from memory for each data access, you're going to have the same problem as I just talked about, but you're going to have it twice over for each instruction. So the page table is cached in this translation buffer, which maps page index to page address. And that works really well, except it's quite small capacity. And for the kind of random jumps through memory that I was showing before, you're going to have to also refresh the translation buffer as well. So if you don't have data locality, you're going to suffer twice over. If you've got really bad data locality, working even within a single page is bad news because you've got the 64-byte boundaries for the cache lines, but you've also got these 4K boundaries, and that'll double the number of cache misses you're liable to. So that's basically the story about how modern hardware works, and this is really important for say VM architects to think about. They think about this stuff a lot because they've got to work in harmony with the hardware. What does it mean for us? Well, what it means for us is that we need to think a bit more about how collections in particular operate than we used to get away with. I mean, my simple idea that you were just going to be able to count the number of instructions that you were going to use doesn't work that well anymore. So for a simple case, let me have a look at a simple case, just traversing a list. And that's obviously order n. If it's a linear, we're going to do a linear search or a linear traverse. And I'm going to look at two things. I told you there are two things that are important, data size and data locality. Let's look at data size first of all and compare a linked list with a primitive array. You may say, well, why am I using a primitive array rather than comparing linked list with ArrayList? Well, I'll explain that in a minute. ArrayList actually suffers from a lot of the problems that linked list suffers from. It's just not quite so bad. So here's what, if you run one way of finding out what's going on with this stuff, and people don't usually analyze cache performance very much for collections. One way of finding out what's going on is to run a micro benchmark using the way that you can read the hardware counters, which tell you how many cache misses there's been. Is one way of doing that is with the Linux program Perf, and you can hook Perf into the Java benchmarking harness, the Java micro benchmarking harness, which is now part of the JDK. So the table I'm going to show you here is one that you could get just by running the JDK from Java 9 onwards on Linux. So for a linked list, I ran it for a linked list with different numbers of elements between 1 and 511. And what you see here is that the performance in terms of the nanoseconds per operation, and an operation is a single examination. It's a Java level operation. In other words, it's examining a single element of the list, and it's going up from 7 for a list of order of length 1K, up to 30 for a list of length 500K. There's nothing linear about that at all. So let's see what's happening. The clock ticks per instruction, which is what hardware people look at in order to find out how well a program is performing, are getting worse. They're not getting worse at this speed, but they are getting significantly worse. So this is a pretty good number. So basically what that means is that on average, a single hardware instruction is getting executed in a third of a clock cycle. And you may be saying, how can that happen? Well, there's instruction level parallelism, so that within the processor, it's actually doing different stages of several instructions at once. Very clever stuff, but I mean, very standard in modern hardware as well. So that means you can get less than 1, and actually less than 1 is what you're looking for. And more than 1 like this is a pretty bad sign. Let's go on and look at things from the point of view of the number of events per Java operation. You see that the number of machine cycles is going up pretty much the way the performance is. No big surprises there. The number of instructions, that's the number of machine instructions for each step of the program, staying the same. It really is. Or this is a perfect example of why time complexity just isn't enough now. Even though this genuinely is order n, and it's very clear that the number of instructions that have to be performed for each step of the program haven't changed. Still, each step of the program is taking a lot longer for a long list than for a short one. Why is that? Well, if we look at the cache misses, we can see that the level 1 cache misses are going up quite a lot. They're certainly going up from between 1 and 7 and between 63 and 511. They're about the same between these two. So you may be saying, this isn't very many cache misses per instruction. Why is it so bad? Well, the reason it's so bad is because cache misses are really, really expensive. And if they go up at all, that's a really bad sign for you. The difference between 7 and 63K is probably accounted for by this by the last level cache. As the list gets big enough, then the last level cache, that's a level 3 cache closest to memory, is also getting hit, as you can see later on. So this is really our problem. What's going on? Well, a linked list has a node size of 24 bytes. This program was not actually run on that MacBook Pro, but on a Core i5 with 32K of level 1 data. Level 1 data cache. Actually, the level 2 and level 3 don't matter very much. Each new list item is 40 bytes because the node is 24 and it's a linked list of integer, so there's 16 bytes for each integer. So overall, we really need to, if we're going to traverse over it repeatedly, we want a cache that's going to be big enough to hold lots of these 40-byte items. But in fact, if it's a 32K cache, we're going to blow it before we even get to 1,000. And what that means is you're going to have to be constantly refreshing the cache, and that's why the performance just continues to deteriorate. So why didn't I compare linked list with ArrayList? Because everyone knows that ArrayList is better. In terms of space consumption, it's much better. The reason is, in fact, it is much better because each new item for an ArrayList is only 20 bytes instead of 40 bytes, because although obviously you've got to you're still going to need 16 bytes for the integer. So I'm kind of cheating here. The array list is much better. But the fact that you're still going to need the same amount of room for the data that the array list is pointing at means that the reduction from 24 to 4 bytes isn't actually going to help you that much. Yeah, you've got an improvement of a factor of 2 in terms of memory consumption, and that makes it better. But it's still going to blow now it's going to blow the cache at 2K items instead of 1K item. Right? I mean, Java's just really very wasteful in terms of the way that it uses memory. And I never used to think this was a problem, by the way. I used to think, well, the convenience of being able to have objects all everywhere, the programming convenience was going to outweigh the okay, so we're using more memory, so why would we care? And actually, most of the time, that is still true. Remember what Knuth said? He said, it's not worth worrying about performance most of the time. Objects are great. But sometimes, as you see, they can be pretty expensive. If we look at the same thing for a primitive array, and now there's no pointers involved at all, you can see it's madly different. But this really is order n. That's because instead of each item each additional item being 20 bytes, like it is for an array list, it's only 4 bytes. So we've got 5 times the space efficiency. So, and as you can see, the cache misses are just great here. So that's an illustration of the problems with just cache size, cache capacity. Second issue that I wanted to talk about was data locality. There's 2 different problems with data locality, because remember what we're wanting to do is make sure that what's been put into the 64-byte cache lines is going to stay valid for a long time. Well, that partly depends on how much of your 64-byte cache line is data that you actually need. Remember, it's got to grab 64 bytes from memory, regardless of what process, well, it's obviously going to be Java, but regardless of what data structure that memory belongs to. If it needs 2 bytes of yours, it's going to get 62 bytes of some other data structure. And if it's got to do that a lot, then obviously you're going to need a lot more cache lines than if your data is closely packed. And the second question is, well, prefetching. Are you giving the processor a chance to help with stride prefetching? So here's a little experiment I ran. I populated a linked list in a natural way. So the idea is something like this. I'm just calculating some integer, and I'm adding this onto the linked list. So if you do that with a linked list that you just leave alone, then typically what will happen is the data will be relatively well packed. I mean, it's still very big, right? But it's reasonably well packed in memory. And then I did something else. I populated it. I call it randomly. And so first of all, what I did was I created an array list, and I used that to and I allocated integers. I populated that with integers. They would be reasonably contiguous. But then I populated the linked list with pointers, with randomly chosen pointers from the array list. So the linked list I was creating was pointing to random places in the block of integers that had been generated from the first program. And then I tried seeing what the performance of those would be. So I'm calling this a demo in inverted commas because it takes about, I don't know what, you can't practically run it. No performance test can really be run in the time that you give a talk. So I have tried doing that, but basically I've got a choice between either keeping talking while a really, really long test goes on, or alternatively running a test that's so short that I have to kind of cover up the standard deviation at the end because you see that it's bigger than the values I've calculated. So my compromise is to run a JMH test and to film it. So this is I only have to talk for as long as it's going to take to run through this. I ran this last night, and I think it took about 3 or 4 minutes, which is too long for a talk. And then at the end of it, you'll see the difference between the natural population of the linked list, traversing the naturally populated one, and traversing the randomly populated one. And the difference is pretty striking. Okay, so really, you can see that just the difference of data locality, we're talking about exactly the same program in every other respect, but just the difference in how the data is allocated to start off with, where it is in memory, gives you a 4-fold difference, roughly, in the performance. So, Right, so, and you know, this is kind of tough on linked list. It's an orphan. Josh Block wrote it. And he says, does anyone actually use it? I wrote it and I never use it. Nobody loves linked list. Okay, so let's talk. I'm nearly out of time. Let me just talk a bit more about some of the data structures. I'm no more experiments to show, but just some kind of illustration. Here's an example of how time complexity doesn't work that well. Another example of how time complexity doesn't work that well. So the way you think about the problems with a hash map is that typically what we worry about most of the time is that we don't get this kind of thing where you've got low collisions. What you worry about is when you get a lot of collisions, and then what you have to do is construct instead of having this nice constant time access, or in theory constant time access to a node on the through just one single level of indirection. If you've got multiple keys resolving to the same hash code, and therefore using the same bucket, you get a picture like this, and everyone will be familiar with this. So here comes another one, and now what you've got is chaining. And prior to Java 8, that would be a linear list. And so in the worst case, a hash map could deteriorate to a linear list. And in the better case, following Java 8, it deteriorates to being a binary tree. And so everybody worries a lot about collisions in hash tables, and quite rightly so, because that affects the time complexity. But you'll now know from what I've been telling you that actually the biggest one, it's quite possible that the biggest overhead in a hash map will be, irrespective of the collisions, the fact that you've got to go and get your data from somewhere else. Data locality is as important as time complexity. So sometimes things are improved a bit. So for example, so in Java 9, we've got these immutable collections, which are kind of a slight addition to the Java collections framework. And what these do is that basically what happens is that the data is organized, the keys and maps, keys and values, the pointers to the keys and values are created at the time that the immutable collection is created. And so these at least are going to have really good data locality. Have I got some code? I've got some code here. Right, so here I've got an example where I've created a map of entries, and map.entry creates a new, for Java 9, creates a new entry object, map.entry object. And it makes an array of these things. So you're clearly traversing over the keys here is going to give you a much better outcome. Of course, it's going to depend on the data locality of these of your actual data. So, I mean, I've actually wondered whether there isn't an argument for saying if you've got a map that you're going to traverse or you're going to actually read from much more often than you're going to write to it, so it doesn't need to be resized. Then, if you can't create it immutably like this, it might be worthwhile, in fact, creating it, building it up however you're going to need to build it up, and then transferring it into an immutable map, because you're going to get better performance out of that in general. I mean, an alternative to that, which is not available in the Java Collections Framework, is to use open addressing, in which the data is actually interspersed with the key value pairs, and that's going to give you really good data locality, because what you do is you just in order to find out where your data is, all you need to do is just step along the array until you find until you find what you're looking for. The problem with open addressing is these things are always a trade-off, and the problem with open addressing is that it gives very much worse performance when the map is heavily loaded. So because you can spend a lot of time searching along the bucket array looking for the keys. But it's a strategy that is used by some other collections frameworks. So doing this talk, I've really come across a lot of collections frameworks. It's really educative. People come up to the end and say, have you heard of? And I said, no, I haven't heard of it, but I'll add it to the slide for the next time. So these third-party collections frameworks often have much better performance than the Java collections framework. There are disadvantages. I mean, the major disadvantage of them is that you've got to learn something else. The Java collections framework was designed to be very learnable. And it really succeeds in that. It's easy to discover. Almost everybody's got their head around it to a reasonable extent. So something like Eclipse collections, for example, which is really good framework is enormous, and you can't learn about it. You can't learn it in the same way as you learn the Java collections framework. Well, I certainly couldn't, and I've been looking at it for a while. So all these third-party collections focus much more on memory efficiency. I don't think that was a huge consideration in 1998 when the Java collections framework was invented. And from the picture that I've shown you, you can understand why it wasn't so important at that time. But since then, it's become more important. And these collection frameworks do all of them. I would like to show you comparative tests, but I haven't run those kinds of tests on this comprehensive set of frameworks and collections frameworks, and I would love to do that. And I'm improving this talk as I go along. So the more experiments are needed. I think these will show better results just because they won't stress the cache capacity so much. But the other issue is, of course, about data locality. So we've got cache capacity and data locality. So a lot of these third-party frameworks support primitive collections, and of course primitive collections are typically going to give you much better data locality. But there are other developments which actually concentrate more on the specific issue of data locality. So the ObjectLayout library, for example, invented by Martin Thompson and Gil Tenney, who are experts in this area. And that is designed to be like it's got really two things in it. One of them is this structured array, which is like a C-style array of structs. So all the data is in there. It's like the immutable map that I showed you, except that instead of key-value pairs, you can have any arbitrary data structure. But of course, it's immutable once it's been created. You can't modify it. And it also will allow arrays as part of objects. So it's very, very much more limited than what you can do in the collections framework. But on the other hand, you get much better performance out of it. Somebody pointed me out, the last time I did this talk, somebody pointed me out roaring bitmaps, which for the right kind of problem is going to be very fast. It uses compressed bitmaps, and you can adapt that to many collections problems. So I'm told, and I believe, that it's very fast. I mean, I've just looked at the benchmarks that they show. They look amazing. But of course, again, you're trading something off in terms of functionality in return for the improvement in performance. So do you want to turn to this first of all? Well, you do if you know you've got a performance problem, but they're probably not for general purpose use. For general purpose use, you'll have to drum your fingers for a while longer on the desk, waiting for Project Valhalla. Now that will be, we used to say it might be in Java 11, but of course now there isn't going to be a JDK 11. So I don't know. Apparently it's coming on very well. Project Valhalla is about value objects, so it will cover some of the same stuff that it's designed to cover, the same area as ObjectLayout, so that you can get, when you have a collection of value objects, they will actually be stored as data. So they'll look to the JVM sort of like primitives, but they'll behave like objects for the programmer. So that's the ambition. And we're also going to get collections of primitives out of that, and some other stuff as well. So Project Valhalla is one to watch if you're interested in this stuff, but it's far from being ready for prime time yet. So that's about where we are. My conclusion, which I've said is a conclusion of sorts, because it's obviously very preliminary, is first of all, I always have to say performance mostly doesn't matter. When it does matter, unfortunately, it matters a lot. Every performance improvement represents a trade-off. You're never going to get something for free, either in terms of functionality or in terms of it only being useful for particular scenarios. Algorithm complexity is still important. So I don't want to suggest to you that you should throw away your textbooks. That stuff still does matter a lot. If you've got an exponential time algorithm, cache complexity isn't going to matter at all. But so are a lot of other things as well. I mean, we always knew that these things mattered. Network performance and garbage collection, resource contention. Those are things that every Java programmer has to deal with all the time. But now I want to add a new one into the mix in your heads, and that is caching as well. So actually, it still is your father's complexity. It's just got more complex than it was. Thank you very much for your attention.